Hi. First of all, let me introduce our group members. My name is Adam Aiman. Next to me is Ismail, followed by Ching, Inshira, and Emma.
Hi, my name is Qing Chung Wei. Today, me and my team member Inshira will explain you the content in the reaction engineering part. The reactor we choose is paid-back reactor, which is PBR. One PBR is using in steam methane reforming (SMR), and another PBR is using in water gas shift reaction (WGS). The reason why we're using PBR is because it is the most suitable reactor for reaction involved catalyst. PBR can hold the solid catalyst in reactor to prevent it flow out with product. PBR will also increase the reaction rate due to more contact during catalytic reaction and have low operating costs. Catalysts we use are nickel-based alumina catalyst for SMR and iron oxide catalyst for WGS process. The presence of catalyst can increase the rate of reaction. Now I will explain how the system works. The system is divided into two parts, SMR and WGS. First, for the SMR process, the methane in natural gas is heated by steam and to create a combination of carbon monoxide and hydrogen. Because the process of steam reforming is endothermic, heat must be added in order to progress. For the water gas shift reaction, carbon monoxide and steam are reacted to create carbon dioxide and more hydrogen. The objective of this process is to increase the production of hydrogen gas. For the strategy to increase the yield and selectivity, first one is decrease the inlet pressure when temperature is constant. Second, increase the concentration of methane. Third, increase the temperature of SMR reaction. And the last one, decrease the temperature of WGS reaction. To propose the sizing of reactor for SMR and WGS, we need to do the stoichiometry table. Inlet flow rate and the conversion of reactor are determined using journal we found. We use the stoichiometry table and calculation to determine the weight of catalyst. After getting the weight of catalyst, we are able to find the size, volume, height, and diameter of reactor. The detail of the calculation are included in the report.
Next, I will present about strategies to purify and maximize the production of purified syngas from crude products coming out from the reactor. First is by gas cleaning. The system did not include the gas cleaning process before entering the reactor, so the molar flow rate of undesired components like nitrogen and methane exists in the total molar flow rate of the system, which can reduce the purity of the syngas. However, the reaction that has been included into the reactor in the system successfully increased the hydrogen production, and the more fraction of undesired product only had small percentage inside the system. Number two, catalytic conversion. When the gas pass through the converter WGS, ion catalyst will cause a chemical reaction that will convert part of harmful carbon monoxide into less harmful gas, which is carbon dioxide. This is because ion catalyst is common catalyst in industrial processes for the Fischer-Tropsch process to convert syngas into liquid fuels. Number three, temperature and pressure control. The heat exchanger in this system can control the feed temperature of the stream. The heat exchanger in SMR used to increase the heat as the catalyst required high temperature, which is 200 degrees Celsius, to maximize the purity. Another heat exchanger was at the feed stream of WGS to lower the temperature, as the ion catalyst need to operate at the lower temperature that lies between 300 to 350 degrees Celsius to increase the purity. However, the pressure in the system for both are constant through the reaction because of when increasing the pressure in the reactor, it will increase the yield of the syngas. By reducing the pressure, we improve the purity of the syngas. Both important elements are very crucial for production. So to maintain the stability of the product, the pressure in the system does not change throughout the processes. And the last one, product separation. In this system, the syngas separation was made using Fischer-Tropsch process that involves the conversion of syngas into liquid hydrocarbon. The ion catalyst that has been chosen as catalyst in this reaction will convert the long-chain hydrocarbon into separated unreacted syngas and other byproducts. Then, using fractionation steps that have been taken inside the reactor, the liquid hydrocarbons can be separated from each other at different temperatures and pressure, as each component has different boiling points and physical properties. Next, the water shift gas WGS that converts carbon monoxide and water vapor into carbon dioxide and hydrogen in the system gradually has increased the hydrogen content of the syngas better than SMR.
Moving on, let's proceed with the process modeling and simulation part. First and foremost is the simulation part. Here, the natural gas from stage 1 is mixed with another water stream and go through a heater and compressor to meet the required temperature as well as pressure. Next, the mixture will go through the first PFR, which the first reaction of steam methane reforming process occur here. Then, the outlet will go through a cooler to decrease the temperature. After that, the outlet from cooler will then go to the second PFR, which the second reaction of water gas shift occur here. Lastly, the outlet here is the final product that we look forward. Now, let's see the error between manual calculation and symmetry part. As we can see, the percentage are quite big here. For example, we take the production of hydrogen that expect to be around 2116.8 kmol per hour, but in experimental only produce 677.19 kmol per hour. This occur because of the different type of flow rate they use. Here, PBR is used for manual calculation. However, PFR is used for symmetry because of no PBR in the symmetry. Next, maybe because of the difference in sizing or we call as volume of the reactor used. Finally is the sensitivity analysis. There are three independent variables involved here. First is pressure. When the pressure increases, the flow rate of hydrogen produced increases. Next is temperature. When the temperature increases, the flow rate of hydrogen produced also increases. Last is feed flow rate. The flow rate of hydrogen produced increases by the increment of the feed flow rate as well.
Okay, next we will proceed to the chapter 4, separation process. In this chapter, we are focused on designing gas membrane separation. In 4.1, removal of contaminant. Membrane separation process is influenced by many factors such as pressure ratio, permeability, stage cut, and selectivity. In pressure ratio, the flow of component across the membrane can only occur if the partial pressure of the desired component in the feed is higher than in the permeate. And then the permeability is property of the membrane that allow the passage of gas molecule in the presence of pressure difference. Next, stage cut. Stage cut is reflecting to the amount of gas permeated through the membrane. And the last one is selectivity, which is the ratio of gas permeability. In 4.2, gas membrane separation. Among all the membrane material that we have discussed, the best method that we can find is the mixed matrix membrane, where it is utilized in combining the multi-wall carbon nanotube and cellulose acetate polymer membrane. This combination is perfect because it will build a membrane module with higher selectivity, high resistance to plasticization, and increase the purity of the selected product. Next, we will move to 4.3, types and configuration. As a summary, each configuration has its advantage and disadvantages, and the appropriate configuration should be chosen based on this factor. So, as you can see on the slide, the most configuration with the green is the most appropriate membrane design. So, as you can see, tubular and hollow fiber has the most appropriate design. So from here, we are choosing the hollow fiber because of the relative cost is low. So therefore, hollow fiber is very suitable for our membrane design rather than tubular.
In these sections, I will explain about the membrane design and module that has been proposed in this project. The first figure shows the cross-sectional area of the membrane cell. The dimension that has been proposed for the inner diameter is 0.625 mm, while the external diameter is 1.5 mm, and the outer boundary diameter is 2.02 mm, which gave us the total cross-sectional area of 3.206 mm squared. The second figure is the membrane module with a length of 1 meter and the thickness of the membrane is 0.5 meter. The third figure shows the block model of the membrane. In this section, I'll briefly explain the calculations of selectivity and flux. For the first calculations of membrane selectivity, we use the ratio of the permeability of CO2 and permeability of CH4, which gave us the value of 56, while the flux we calculate using these equations right here, which is the permeability over thickness multiply with the driving force, which is actually the pressure difference. And we gain the flux for CO2 and CH4 right here.